Number 16 on page 79. Find the limit if it exists. And then they give us what's called a piecewise defined function. It's defined in pieces. The function equals one equation for a certain interval. It equals a different equation for another interval. And sometimes there's 3 or 4 pieces. This one has 2. We're supposed to find the limit of f of x as x approaches 2. And our definition of f of x is this. F of x equals x squared minus 4x plus 6 whenever x is less than 2. And it equals negative x squared plus 4x minus 2 whenever x is greater than or equal to 2. All right. Now, if we were trying to find the limit for some number other than 2, let's say we're trying to find the limit as x approaches 10. I could completely ignore that, couldn't I? Okay? If we were trying to find the limit as x approaches 0, I could completely ignore that. But since we're finding the limit as x approaches 2, I need to use both definitions of the function, because I'll use one of them as x approaches 2 from the left, and I'll use the other one as x approaches 2 from the right. Okay? So what we're going to do is set up 2 different one-sided limits. If you recall definition from yesterday, for the limit to exist, the limit from the left and the limit from the right have to equal each other. So that's what we're going to find out. We're going to find the limit of f of x as x approaches 2 from the left. Then we're going to find the limit of f of x as x approaches 2 from the right. And we'll see if they're equal. If they're equal, that's what the limit is. If they're not equal, then the limit does not exist. It's as simple as that. So, finding the limit as x approaches 2 from the left. Use the definition of the function where the x coordinates are to the left of 2. Well, aren't those the numbers that are to the left of 2? The ones that are less than 2? All right? So that's the definition I use. So I'll make that the limit as x approaches 2 from the left of x squared minus 4x plus 6. And I can use substitution on that. There's no reason not to. So use substitution. Replace x with 2, you simplify it, and you get 2. All right, next, let's do the same thing on the other side. It's the limit as x approaches 2 from the right. Well, those are the numbers that are to the right of 2, aren't they? I don't really care that the or equal to is on there. Okay? X greater than 2, those are the numbers to the right of 2. So that's the definition I use. So I'm finding the limit of negative x squared plus 4x minus 2 as x approaches 2 from the right. I substitute 2 in for x because there's absolutely no reason not to. And it turns out that the left-hand limit, that's the limit as x approaches 2 from the left, does equal the right-hand limit. That's the limit as x approaches 2 from the right. Therefore, that's the limit of f of x as x approaches 2. So our final answer, the limit of f of x as x approaches 2 equals 2. How cool is that? It actually is, I think, because it seems difficult, doesn't it? Oh my goodness, we have this function with 2 different definitions. This must be complicated. It's not. It's not complicated. It's 2 problems in one, but it's not complicated. Alex? Not really, because you might have that as one of your graphs, and okay, so let's say it stops at 2, so it does that, and then the other graph might be like that. They may not touch at all. Okay, So what we've got going on is we've got a parabola, and then the other parabola connects to it. Okay? But there's no rule that says they have to connect. Now we know they do. Okay? Exactly. That's the interesting point. All the others are boring. We know the limit of a polynomial is going to exist throughout its domain. So we just got to see if they connect up. Okay? That's all we're doing. And since they do connect up, since that limit from the left does equal the limit from the right, this function is continuous everywhere. We knew it was continuous for all the numbers less than 2 because it's a polynomial. We knew it was continuous, get rid of the or equal to, for all the numbers greater than 2 because it's a polynomial. What we didn't know is it continuous at 2? Now we know. It has to be continuous at 2. That help? Yeah. Let's take a look at 21. That is the limit of 3 times the greatest integer of x minus 5 as x approaches 4 from the left. Now, if you recall, all of the theorems that those mathematicians took so long to figure out about evaluating limits end up saying that, for the most part, if substitution gives you an actual real number, then you can find the limit by using substitution. Well, okay, so I'd like to stick a 4 in there. But it's not quite that basic, okay? I'm gonna stick a 4 in there, but I got to pay attention to which side those numbers are approaching for. They're approaching from the left. No, not -4, but 4 from the left. So it's 3. The greatest integer of a number that's approaching 4 from the left is 3. We would actually have trouble. We couldn't work. If they didn't put the negative sign, meaning from the left, we would actually have to set this one up like we did number 16 and find the limit from the left and the limit from the right and see if they meet. Because one thing, you remember at the beginning of the year I said you need to have a basic knowledge of what graphs are going to look like without graphing them. One thing you need to know, anything involving the greatest integer function is going to be a step. Okay? Now we can move the breaks in the step around by multiplying by something or dividing by something, but we're going to have breaks. So if it's not a one-sided limit you're finding, you'll need to set it up as 2 different one-sided limits. Okay? Eric? Here's what you need to think of it. Here's what you need to think. Since that's the greatest integer of x, as x approaches 4 from the left, think of it as x is 3.9, then 3.99, and then 3.99999, right? What's the greatest integer of those numbers I'm saying? It's always 3. So we're kind of doing substitution and we're kind of not. Okay? We're thinking, okay, x is approaching 4 from the left. I mean, I can stick in a 3.9, and the greatest integer of that is 3. I can substitute in a 3.99, and the greatest integer of that is 3. Okay? Exactly. So, okay. All right, let's see what I've got written here. The greatest integer of x, as x approaches 4 from the left, is 3. Look at a number line. There's 4, there's 3, I'll even throw 5 in over here. X is approaching 4 from the left of 4. So x is here. What's the greatest integer of whatever that number is? 3. Then we move x a little closer to 4. What's the greatest integer of whatever that number is? 3. What's the greatest integer of that one? 3. That one, 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 3. Yes, because it's the greatest integer function means greatest integer less than or equal to whatever your number is. So the greatest integer less than or equal to all of those numbers is 3. No, but we'll do that in a second. We'll do that in a second. So you with me that it's 3? Okay, so the limit can be found. So I am kind of substituting once I've figured out how that greatest integer function works. So figure out how the greatest integer function works, then do the substitution, and then you can find your limit. Okay? So we know that as x approaches 4 from the left, the greatest integer of that will be 3. So replace the greatest integer of x with 3, and then evaluate what you get. So what's our final answer? Yeah. Now, let's talk about what would be different if we changed the problem. That wasn't the problem, but this was. If it was the limit as x approaches 4 from the right of 3 times the greatest integer of x minus 5. If x is approaching 4 from the right, there's x, then it gets closer to 4, closer to 4, closer to 4. What's the greatest integer of all those points I just put up there in black? It's 4, not 5. The greatest integer is the greatest integer less than or equal to a number. So that would work out to be 3 times 4 minus 5. Make sense? Okay. Let's take a look at 30. This time the directions say, discuss the continuity of the function on the closed interval. All right, on the closed interval. So, something I didn't get to yesterday was defining continuity on a closed interval. We had continuity at a point. We had continuity at an open interval. This question asks us about the continuity of a closed interval. So, let's look at page 73. And the book says, the concept of a one-sided limit allows you to extend the definition of continuity to closed intervals. Basically, a function is continuous on a closed interval if it is continuous in the interior of the interval and exhibits one-sided continuity at the endpoints of the interval. All right, one-sided continuity. Okay, I mean, we're getting deep in the weeds here, okay? I lose a lot of folks about this time, so stay with me. Don't check out. Stay with me here. All right, if that was an open circle and that was an open circle, wouldn't we say that that function's continuous everywhere between A and B? Okay, there's no holes, there's no asymptotes, there's no gaps. It's continuous. Now, if we put the endpoints on there, we want to be able to say whether or not this function is continuous on a closed interval. And here's how you figure it out. Find the limit of f of x as x approaches a from the right. Do you see why you have to approach a from the right? As far as we know, this function does not exist to the left of a. We're not looking at anything else. There might be a lot more to this graph. That may be the entire function. But we're just looking from A to B. So from A to B, we've got to move x closer to A from the right of A. Now remember that our definition of continuity at a point was that the limit at that point equaled the value of the function at that point. All right? So we can't find the limit as x approaches A, can we? Because the definition of that says that the limit from the left and the limit from the right have to equal. There is no limit from the left. It doesn't exist on this interval. So you have to find the limit from the right of A, and it has to equal the value of the function. Then we do a similar thing at B. The limit from the left of B has to equal f of B. Yes. So this is mostly mathematicians being picky, but they got to be picky, right? They didn't land that thing on Mars the other day by just thinking, good enough. They had to be really picky. So you've got to be. So we've kind of taken, I think, a simple idea and made it look really complicated when you write out the math. But it has to be that way because they have to be consistent with their definitions. Okay? You can't change a definition to suit you. Now, I can in a class to clarify a concept. They can't when they write a book. They've got to make it mathematically correct every sentence they write, don't they? Now, you and I can paraphrase so that we clarify things. But a paraphrase isn't as good as the exact thing. Okay? So the paraphrase is this. A function is continuous on a closed interval if it's continuous on the open interval and the limit as x approaches each endpoint equals the value of the function at each endpoint. Okay? Because remember continuity, just pick a point in here, call it C. The function is continuous at C if those three conditions are met. The limit as x approaches C exists, the value of f of C exists, and the limit as x approaches C equals the value at C. So, if we know it's continuous on the open interval, we know that's true for every C you could pick out. It can't be true of the endpoints because the limit at the end technically does not exist because you can't get it coming from the other side. You see what I'm saying? That's why they go back to these one-sided limits. But if they didn't have to go back to those one-sided limits, it kind of makes sense, right? The value at f of A equals the limit as x approaches A. It's just that it has to be from the right. And f of B equals the limit as x approaches B. It's just that that limit must be from the left. Did I beat a dead horse? Or maybe I've revived the horse? Could be. Wouldn't that be fun? Might be fun. You don't know. You've never done any. We'll see. Right now, understand the concept. Then we'll work on situations as they arise. All right, so back to number 30. Discuss the continuity of the function on the closed interval. All right, so first let's talk about between -3 and 3. If t, instead of x, if t is a number between -3 and 3. So pick any number between -3 and 3, not including -3 or 3. Any number in the open interval. 0, -2, 2, 2.9, -2.9. Any of those numbers, when you square it, it'll be a number less than 9, won't it? Yeah. Right? So the square root of 9 minus a number less than 9 exists. Because what's the only thing you really got to worry about under a square root sign? Negative. Don't want a negative. So our function's continuous between -3 and 3 because we always get a positive number for our radicand and we can take square roots of positive numbers. So then we test the endpoints. What if I put a -3 in there and square that? What do I get? 9. 9 minus 9 is 0. Does the square root of 0 exist? Is it a real number? Yes, it's 0. So I'm good at -3. Am I good at 3? Yeah, because of the same reason. So what's your conclusion about the continuity of this function on that closed interval. It is continuous. Now, without using the limits and all that, that's fairly intuitive, right? Or just for me? Now, here's where you'd have to watch out. Okay, so we're good with the way it is? All right, let me mess with you. Let's make the interval from -4 to 3. See, now we're in trouble, right? The function's continuous from -3 to 3. We just figured that out. But if we try to number like -4 or -3.9 or even -3.1, when we square those, we get a number bigger than 9, and 9 minus a number bigger than 9 would be a negative number, and all of a sudden the square root of that negative number is not a real number anymore. So if that was the interval they had given us, we'd have to say something like, well, f is continuous on the closed interval from -3 to 3, but discontinuous from -4. We would say it's discontinuous from -4 to 3. How's that? Closed on one end, open on the other. Oops, negative. And it would be non-removable because the function just flat out would not exist for those numbers. Do what? That's right. You're trying to find the boundaries. Okay? Make sense? All right. I think that was the only one there. Okay. All right, let's keep going. Properties of continuity. On page 75. Now, we've studied properties of limits. Properties of continuity are similar. Shouldn't be real surprising because don't you have to talk about limits to really talk about continuity? Okay? So, here in the little box, if you have a continuous function at a certain point, okay, and remember, if it's continuous for all the points in an interval, it's continuous on that open interval, and then we just learned how to figure out if it's continuous at the end points of a closed interval. So, think of this either as continuity at a point or continuity on an interval. It works the same. If you've got a continuous function and you multiply it by a constant, you'll get another continuous function. For instance, if you had a polynomial function, and you multiply the whole thing by 2, the result would be another polynomial function, and it's going to be continuous also. Okay? Some are different. If you have two different continuous functions and you either add them together or subtract one from the other, the result is a continuous function. Like if f of x was x squared and g of x was x, if I add those together, I'll get a polynomial. It'll be continuous. If I subtract one from the other, I'll get a polynomial. It'll be continuous. Same thing if I multiply them. If I multiply those two together, I get something that's continuous. Okay? Same thing if I divide them, except for where the denominator equals 0. Okay? Because if I did divide, right, I could actually simplify that. But before I simplify it, there's a discontinuity at 0. I can remove it by dividing out. So as long as your denominator does not equal 0, the result is continuous. These things are always are continuous for every point in their domain. Polynomial functions, rational functions. Now, every point in their domain. Because for a rational function, you have to kick a few numbers out of the domain sometimes, don't you? The ones that make the denominator equal 0. So it's continuous everywhere else, just not where the denominator equals 0. Radical functions are continuous unless it's a negative number under a square root, or a fourth root, or a sixth root, an even numbered root. Do we mind negatives under a cube root? No, they're fine. Trig functions. So almost every function we deal with is continuous throughout its domain. So that's not always the case, because, I mean, how boring is that? They give you 15 problems in a row and ask you about their continuity, and you say continuous everywhere, continuous everywhere, continuous. It gets boring, right? We're more into interesting. That's one reason they'll give us piecewise functions, and that's the reason they'll give us functions with denominators. Rational function. It doesn't even have to be a rational function. It can be a square root. It can be a radical with a denominator. Okay, just things with denominators and piecewise defined, things where you have to worry about negatives under even roots. Those are the things that we consider interesting. Okay? Continuity of a composite function. If you have two continuous functions at a point, and you make a composite function out of them, the result is continuous at that point. Okay? And well, yeah, I guess I will. So one consequence of this fact is that if f and g satisfy the given conditions, what are the given conditions? G is continuous at C, and f is continuous at g of C. Okay? Then you can find the limit of f of g of x as x approaches C by just substitution. Okay? And I think I'll stop before we do the intermediate value theorem. All right, let's look at 34. Back on page 79. The directions say, find the x values, if any, at which f is not continuous. Which of the discontinuities are removable? All right, for number 34, we've got a denominator, so it's a rational function. There aren't any square roots, no trig. This is a rational function. Rational functions are continuous throughout their domain. So in other words, we're looking for what numbers are not in the domain. What numbers could replace x and make the denominator equal 0? Are there any? There aren't any. Because if you take a number and you square it, you always get 0 or positive, right? You never get a negative. So a 0 or a positive number plus 1, so that's never going to equal 0. So the denominator never equals 0. So this function is continuous for all real numbers. That was boring, continuous everywhere. Let's try one a little better. Number 40. All right, most of you already see 3. Where else is this function discontinuous? Negative 3. If you're having trouble seeing that, that's okay. Just factor it out. Factor the x squared minus 9 and turn it into the quantity x plus 3 times the quantity x minus 3. And now you'll see there are two different numbers that can make the denominator equal 0. If x equals 3, then that second parenthesis becomes a factor of 0. If x equals negative 3, that first parenthesis becomes a factor of 0. So negative 3 and 3 make the denominator equal 0, so this function is discontinuous at negative 3 and 3. Yes? That's what we're going to do next. So the first question was, where is this function not continuous? Two places, negative 3 and 3. So f is discontinuous at x equals negative 3 and at x equals 3. And you don't have to write what I wrote in the parentheses. That's for your notes, so you'll understand why, since they make the denominator equal 0. But then the second question is, which of the discontinuities are removable? Well, okay. So we're sitting here like this, right? Can I remove a discontinuity? Divide those two factors out, and now we have a function that agrees with the original function at all but one point. And this function is only discontinuous at -3. This function's continuous at +3, isn't it? We removed the discontinuity at +3. So the discontinuity x equals 3 is removable. Therefore, x equals 3 is removable, and x equals -3 is non-removable. Removable, non-removable. Still good? 45. Same directions. Find where the function is not continuous, and if you have any, which discontinuities are removable. On 45, the top piece, f of x equals x, that's a line, so that's continuous throughout its domain. The bottom piece, f of x equals x squared, that's a parabola, so it's continuous through that domain. So all we need to check is, do the two different graphs connect up when x equals 1? That's what we need to check. Okay? So, how do you think we might decide whether or not the two functions, well, let's write this down before we do that. The only possible discontinuity is at x equals 1. We can graph them and do it. We can make a table. We can do lots of things. But here's what we're doing. The value, what is the value of this function when x does equal 1? Where are you plugging it in, top or bottom? Top. The top because of the or equal to. Okay? Now, in this case, we'll get 1 either way, which makes me think we've probably got a continuous function. Okay? All right. But we're gonna prove it because it's not always going to be that obvious. So f of 1 equals 1. So we need to see if the limit as x approaches 1 is also equal to 1. Because that's our definition of continuous at a point, right? That the value of the function exists, that the limit of the function exists, and that the limit equals the value. So that's what we're going to find out. We're going to find that limit. Well, we're going to try to find that limit and see if it equals 1. Since it's a piecewise defined function, and each piece has a different definition, we have to approach this with one-sided limits. We need to find the limit as x approaches 1 from the left. We need to find the limit as x approaches 1 from the right. And if we want our function to be continuous, we're hoping that both of those equal 1, aren't we? To find the limit as x approaches 1 from the left, use the definition of the function that have the numbers to the left of 1. The numbers to the left of 1 are these, aren't they? So that's the definition I use, x. Well, what's the limit of x as x approaches 1 from the left? 1. Then we find the limit of f of x as x approaches 1 from the right. We have to use the other definition because those are the numbers to the right of 1. So we're finding the limit of x squared as x approaches 1 from the right. Substitute and you get 1. Therefore, the limit of f of x as x approaches 1 does equal 1. And what's that tell us about the continuity of this function? It's continuous for all real numbers. Everywhere continuous. No discontinuities. However you want to say it. continuous on the interval from negative infinity to infinity. I think we'll stop there. All right, let me piece together two different assignments here. All right. You've already done 1 through 14, 25, and 27. So let's do 15 through 24, 29, 31. No, I'm not going to stop there. And 33 through 53 odd. Yeah, I know.